So section 1.4 in college algebra is going to introduce you to, or reintroduce you to, the transformations of certain graphs of functions. These are, again, old concepts from Algebra 2. We're just going to take it up a level. And this might be a new concept for most of you. We have functions that can be considered even or odd. And they are even if when you take the function and you evaluate it at negative x, it comes out to the same exact function that it used to be before. It also has symmetry with the y-axis. So a clear example of an even function would be if you had a parabola, oops, pretend it was centered at the origin, because apparently I can't graph. But notice, if it was drawn well, you would have a split down through the y-axis, and we'll show you how to test it algebraically, whether it's even or odd, in a minute. An odd function is a little different. If you take your function and you plug in or evaluate at a negative x, you're going to not end up with the original function. Instead, you're going to end up with the opposite of your original function, which is called negative f of x. And he has symmetry with the origin. So an example of a graphical representation of something that is odd or has symmetry with the origin would be, I'm supposed to go through the origin, sorry, a cubic polynomial that's centered at the origin. So let's talk about how to test these algebraically. If we have the function x to the third power plus x, and I asked you, what do you think it is, even or odd? Most of you would say odd, simply based off of the degree of the polynomial, and that's what you probably want to do. So we're going to test to see if it is odd, and remember, if it's odd, that means when you take your function and you evaluate it at negative x, he should come out to negative g of x, and let's see what happens. So g of negative x. Go up to my original function, and instead of x to the third power, it's negative x to the third power, and then plus a negative x. And if I simplify that, negative x to the third power is just negative x to the third, and then plus minus x is minus x. When I compare that to negative g of x, which would be my g with a negative out in front of it, notice what that does is it just switches everybody's sign. And you should now notice that, yes, indeed, those are the same. So yes, this is an odd function. Kind of an interesting way to use an algebra proof. It's not an official proof, but this is good enough for me. So number 2, our new function is x to the fourth plus 3x squared. And if you had to take a guess, I'm thinking most of you would think maybe this was an even function. And we're going to go ahead and test it. So remember, if it is an even function, that means when I evaluate him at negative x, he should come back and give me the same exact function that I started with. So let's try that. When I evaluate my function at negative x, I would get negative x to the fourth power plus 3 times negative x squared. And when I simplify that, negative anything to the fourth power would turn out to be a positive x to the fourth power. And then same thing, 3x squared. And you would notice that this guy and the original match, so yes, this is an even function. Number 3, if I looked at the original function, I'm thinking fifth power, I'm thinking maybe it's odd. So let's try that. I know if it's odd, when I evaluate my function at negative x, he should come out to the opposite of my original function. So let's see if that happens. H of negative x would be negative x to the fifth power plus 1, which would simplify to negative x to the fifth power because of the odd exponent, but still a plus 1. Now, contrary to that, I think if I was to take the opposite of h, which is negative h of x, that would be negative and then x to the fifth plus 1 in parentheses, and when I change everybody's sign, you'll notice the negative 1 is not the same as the positive 1, which means that we do not have an odd function. And I also noticed that when I evaluated it at negative x, he does not come out to the same as the original, so he's not even. So this guy is neither even nor odd. And transformations, this should be all old. So if I have our standard cubic polynomial of x to the third power, hopefully you remember that x minus 2 to the third power, that's a horizontal shift. Remember the general form. is x minus h squared, cubed, cubed, and that could be plus a k. There's also an a in front. We'll talk about that in a second. The horizontal shift is kind of opposite of what it appears. So when it says x minus 2 in the parentheses, we realize that that's actually a shift of right 2, and you could confirm this on your calculator. So on number 5, x plus 4 to the third power, that's actually a shift of left 4. X is a third, and then outside of the parentheses plus 5, that's a vertical shift, and the k does exactly what it appears to do. So up 5 is number 6, and therefore number 7 is down 2. And then when they throw a negative in front of the x, what that does is it reflects the function over the x-axis. So you're going to write all that out. Reflection over the x-axis. Don't just write reflection, you have to refer to the x-axis as well. Now when they put a 4 in front, we call that a vertical stretch of 4. So it's going to raise up your y values by a factor of 4. It's going to stretch them up and also down. And they put a 1/2 in front. It's still technically called a vertical stretch, even though it's shrinking it really. But if you say a vertical stretch of 1/2, that's acceptable to me. What that actually means is it shrunk it by a factor of 2. And then number 11 puts 3 things together. We've got a shift that is right 1. We've got a shift of up 2. And we also have a vertical stretch of 3. That should seem very familiar to you. Alright, number 12. We live in the day of the graphing calculator, so I realize you guys will likely fill out this t-chart using your graphing calculator, and that's fine. But if I were to take a -2 and plug it in even with my head, which we could easily do, we'd get a 4. Here you'd get a 1, then a 0, then a 1, then a 4. And when you plot all these points, you're going to end up with a really lovely quadratic, which is going to be, it's hard for me to graph on this tablet, so apologies. And the domain of this parabola is -infinity to infinity. In the next example, it's a cubic polynomial, which if you remember what this looks like, that would help. -2 raised to the third power is -8. -1, 0, 1, and 8. So when I go ahead and I graph this, and of course using a graphing calculator will give you a little better picture, although I will say my calculator doesn't do an awesome job of graphing this. He goes like that, and polynomials always have a domain of -infinity to infinity. So they go forever to the left and forever to the right. The absolute value function, when I fill out my t-table, I get a 2, a 1, a 0, a 1, a 2, and when you plot absolute value, you're going to notice that it's like they had a line, and the lower part of the line got reflected up over the x-axis so that he was positive, and it creates what looks like a V-shaped graph. Notice this is very different from the parabola. This is V-shaped as opposed to the parabola, who was U-shaped. His domain, however, is still -infinity to infinity. 15 is our first introduction to a new kind of function. If I was to plug in a -1 for the square root, and you did see this in Algebra 1, if you did it on your calculator, you'd notice he gave you an error. That's because he does not exist under the real number system. The square root of -1 would introduce an I, and we're not going to graph an I here in this class. But when I put a 0 in, we start getting values. 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So the first point I'm able to plot is 0, 0, 1, 1, 4, 2, whoops, and 9, 3. And then the square root graph starts, in this case at the origin, and kind of does a curve slightly upwards, but his domain does begin at 0 with a bracket and then forever to the right. You do have to have what these graphs look like totally memorized. We are going to take a little short functions transformation quiz that you cannot use your calculator on. Okay, the cube root of -8 is -2, -1, 0, 1, and 2. So when I plot these points, you'll start to get a picture of what this looks like, and this is important that you have it memorized, of course. So this is my least favorite one to graph, especially on my tablet here. something kind of like this. Now the domain for sure stretches from negative infinity to infinity. All polynomials do that. And then, this is a boring one. This is just going to be a line with a slope of 1 through the origin. Oh my goodness, could have done this when you were little kids. Whoops. Pretend I hit all those points. And the domain, of course, is negative infinity to infinity. So, this is a parabola, and it has been shifted up 2 units. So remember, the parabola used to start at the origin, but now he's going to start at up 2 units. You could get some more accurate points off of your calculator's table or just knowing it in your head, but for now, let's just sketch it in. Parabola opens up like this. His domain is still negative infinity to infinity. That has not changed. Now this is the cubic function, which I'm going to lightly sketch in what he looked like for you. Remember, the cubic function looked like that, so it wiggled through the origin. But since he was shifted right 4 units, this origin wiggle is going to be over here now. And again, I'm just going to sketch it in, but it does look something like that. You would get more accurate points off your calculator. Domain is still negative infinity to infinity. Now this last function, the square root function, remember when I graphed the original mother function, it kind of looked like this. So my new function, which obviously has been shifted left 5 and down 4, this origin beginning point has been shifted left 5 down 4. Oops. And then we're just going to kind of sketch it in. You would get more accurate points off your table. His domain is not negative infinity to infinity because he definitely starts, and that is affected by his transformation. So his domain is negative 5 to infinity. I have not asked you about range on any of those, but I could. The absolute value graph, remember, is supposed to be like a V shape like this. Oops. But this guy has been shifted right 2 units, and then this negative means it was reflected over the x-axis. So this origin point actually starts right here at 2, and then instead of going up 1 over 1, he's going to go down 1, left 1, down 1, right 1. And that is my new function. Domain is negative infinity to infinity. It does go forever left and forever right. Now to the 1/3 power, that's the same thing as saying it's the cube root of x plus 1. So if you remember what a cube root function looked like, the mother graph of it looked kind of like that. So I'm going to sketch this in. He's been shifted, let's see, left 1, and he's got a vertical stretch of 4. So instead of going through the origin, he goes through right here at negative 1, and he's going to go down and up much faster. So again, accurate points on your calculator, but that's good enough sketch for me today in college algebra. And then this square root graph was supposed to look like this, but he's been shifted right 5, down 3, and then interesting, we've got a vertical stretch, but it's technically a shrink of 1/2, which even though he's hardly going up at all as it is, he's going to go up even slower. So let's see here. Right 5, down 3, and then hardly going to go up at all. And again, more accurate points on your calculator. His domain, however, has been affected. Whoops, not negative 5, positive 5 to infinity because he was shifted right 5. Oh, I don't think I ever did domain back on this guy. He was negative infinity to infinity. And this one's fun. I'm going to give you a function that's kind of like a piecewise, well, it is a piecewise function, and it's got all sorts of discontinuities and jumps and holes. And this is f of x, and I want you to graph 2 times x, f of x minus 1. Now, if we think about what transformations that means, we've been shifted right 1 unit every single point, and then we have a vertical stretch of 2. So what I'm going to do is I'm going to look at the endpoints and figure out who they are and kind of adjust them from that. So this is the endpoint of negative 6, 3. And this is the endpoint negative 3, 3. And if I think about shifting everything right 1 unit and then stretching it vertically up or down, in some cases 2 units, multiplying the y value by a 2, what that's going to do is make my new point negative 5, comma 6, because I shift right 1 unit, so negative 6 to negative 5, and then stretching my y's by a factor of 2. So this guy's going to become negative 2, 6. So let's plot those points. Negative 5, 6, and that was a filled in circle originally. And then negative 2, 6, and that one was an open circle. And they connected in between. Alright, this point right here is originally the point negative 3, and this open circle here is the point 2, 2. And if I think about applying these transformations, if I shift right 1, that's now going to be a negative 2, and then stretching this vertically is going to actually multiply it by 2, which gives it a negative 6. It's going to pull it down by a factor of 2. And then this guy, if I shift right 1, will now be a 3, and then multiplying this by a factor of 2 will be the point 3, 4. So negative 2, negative 6 as a closed circle, and then 3, 4 was my open circle. Alright, almost done. Closed circle here, closed circle here. So originally this was 2, negative 2, and this was 6, negative 2. So when I apply these transformations, shifting it to the right, and then stretching it by a factor of 2 gives me the point 3, negative 4. And then this, shifting to the right, would be 7, stretching by 2 would be a negative 4. Let's go ahead and plot those. And then 7, negative 4. Those are both closed circles, I believe. Connect. So you'll notice the shape looks really similar. The diagonal segment in the middle looks a little steeper because it was stretched by a vertical stretch of 2, which for a line means the slope has been multiplied by 2. The horizontal pieces don't look too different. They're just higher or lower depending on where they originally were, and they were shifted definitely to the right one. Alright, that's 1.4. Lots of good review.